Welcome to The Explainer. Today, we're doing things a little bit differently. We're going to deconstruct one incredibly powerful moment, a moment captured in solid steel and flowing liquid. We're taking an everyday object and breaking the whole thing down to reveal the hidden symphony of physics and industrial design that actually makes it tick.
You know, it's a question we rarely ask ourselves when we're just trying to make breakfast, right? But before we even get into the pure mechanics of it all, I want you to just consider the invisible physics required to effortlessly extract liquid from a solid piece of fruit, using literally nothing but human hands. I mean, it feels easy, doesn't it? But mechanically speaking, it requires a massive, massive multiplication of force. What we're looking at right here is a frozen snapshot of pure mechanical advantage in action. You've got the sleek stainless steel, the super tight grip, and the immediate explosive result of that applied pressure. It is definitely not just a kitchen tool. It's a highly engineered machine designed for one specific, incredibly forceful task.
Okay, moving right into section 1, the power in your hand.
Notice the way the hand just naturally wraps around those curved upper and lower metal handles. The designers didn't just slap some flat pieces of metal together and call it a day. No, these are smoothly contoured to fit the exact natural curve of your palm and fingers. It's absolutely crucial, because this ergonomic choice means that when you push down, all that focused energy transfers efficiently into the tool without hurting your hand or, slipping right out of your grasp.
And this brilliantly highlights the dual nature of the design. Just look at the push and pull relationship happening between the two arms. That bottom handle, the one supported by the thumb and the base of the palm, that anchors the entire device. It's your stabilizing foundation. Meanwhile, the fingers are wrapped around that top handle, acting as the dynamic driver, pressing down. It is a perfect, controlled balance of pressure.
Which brings us nicely to section 2, anatomy of the lever.
So those long stainless steel handles you're holding, they're acting as levers. Specifically, it's a classic second-class lever system. Think of a wheelbarrow. In this type of system, the load sits right between the fulcrum and the applied force. So, by extending the handles way back from the crushing mechanism, the device drastically multiplies your physical input. A relatively light squeeze at the far end of the handles translates into an immense crushing force inside the chamber. It's brilliant geometry, really, saving our muscles from doing all the heavy lifting. But as you might guess, a lever is pretty much useless without something to pivot against. To make leverage actually work, you need a highly durable pivot point. And that brings us to a microscopic look at the very front of the device. Honestly, the unsung hero of the whole operation.
Take a really close look at that thick, riveted metal hinge right at the far left edge. That is our fulcrum. Every single ounce of that multiplied force your hands are generating, it ultimately bears down on this one specific joint. That is exactly why it's heavily riveted and bolted through thick steel. If that fulcrum fails, well, your mechanical advantage vanishes instantly. It all happens so fast, but in a fraction of a second, 4 distinct sequential steps are playing out. You apply the grip, the back levers engage the front hinge, the internal press drops down to compress the chamber, and boom, that immense pressure forces the liquid to release. It's this rapid-fire chain reaction of applied physics, turning human intention into immediate mechanical output. All right, let's shift gears down to section 3, the extraction chamber.
This sturdy, cylindrical chamber right in the middle is the absolute heart of the operation. Notice that horizontal groove stamped right into the side of the metal? Well, that's not just there to look pretty. That groove adds vital structural integrity to the thin steel wall. It actually prevents the cylinder from buckling or warping outward when that crushing pressure hits its absolute peak. And using stainless steel here? Incredibly intentional. Not only does it have the tensile strength to handle those compressive forces without bending out of shape, but it's also highly non-reactive. It effortlessly handles the intense acidity of citrus juice without corroding or transferring metallic flavors, perfectly protecting both the tool and your morning drink. So when you step back and look at it, all these distinct industrial design choices are working together in perfect harmony for one singular goal. The curved grip, the riveted pivot, the rigid steel, that reinforced cylinder wall, and the multi-hole drainage. If you remove or even cheapen just one of these elements, the whole thing falls apart. The tool either breaks, hurts your hand, or just utterly fails to get the juice out.
And that leads us to the final payoff in section 4, form, function, and yield.
Just witness the pure efficiency of the strainer plate hidden at the bottom of that cylinder. You get these multiple, rapid streams of clear, yellowish liquid effortlessly escaping the high-pressure zone. Those holes are sized perfectly to hold back the fibrous pulp and seeds, all while letting the juice evacuate instantly. It is, quite literally, a waterfall of efficiency. So the big takeaway here is that the seemingly ordinary kitchen tool is actually a masterclass in functional industrial design. It takes your raw physical input, multiplies it through geometric leverage, redirects it through a reinforced pivot, contains the whole reaction in a structured cylinder, and filters the result flawlessly.
The visual journey of all that mechanical force ends beautifully, pooling right into a clear glass bowl. I mean, the contrast between the rigid, forceful industrial steel up top and that smooth, calm liquid down below, it's just a perfect testament to what well-applied mechanics can actually achieve.
So, it leaves me wondering, what unseen engineering is hiding in your kitchen right now? I really hope this explainer inspires you to look just a little bit closer at the everyday tools around you. We so often take for granted the brilliant physics resting right in our own drawers. Next time you effortlessly squeeze a lemon or pop off a bottle cap, take a second to marvel at the incredible mechanics hiding just beneath the surface. Thanks so much for joining me on this deep dive, and as always, keep questioning how the world around you actually works.